larger than it subtends a larger angle in the sky. That's quantifiable. And we can quantify that in this equation. The size of something, S, is proportional to the angle it subtends in the sky times its distance from you, R. And this is just very useful. And we went through some examples last time. Basic idea is if you know 2 out of those 3, you can find the other one. If you know how far something away from you is and its size, like say the moon, that was this example, then you figure out the angle it subtends in the sky, which is about ½ a degree. Okay. Remember, we mentioned that if you put your full arm length out, your tip of your finger will subtend about 1 degree in the sky. So the moon is about half that. Okay. And you can rearrange that equation to find, if you know the angle of something and you know how big it is, then you can figure out how far away it is. Or if you know how far away something is and the angle it subtends in the sky, you can figure out the size. Okay, so this is very useful. Just one of those things that we use all the time in astronomy. And I mentioned again that like your fist subtends about 10 degrees, your tip of your finger about 1 degree, and we'll talk a lot about it, but the sizes of astronomical objects in terms of the angle they take up in the sky. So one of the largest things, if you look out in a nice dark night sky, is the Large Magellanic Cloud. That's a satellite galaxy to us. And it's about a fist size in the sky, about 10 by 10 degrees here. The Andromeda Galaxy, really enormous. It's about 3.5 by 1 degrees. In other words, from here to here is about 6 moon widths, more than 3 degrees. Okay? And you'll also see using arc minutes. Remember, there are 60 arc minutes in a degree, so the Orion Nebula. Now, this is one of these beautiful cloudy nebulas that it's hard to see with the naked eye because you need a really, really dark sky, and usually the photographs you see are time exposure photographs. But 65 arc minutes, that's a little bit more than a degree. There's all sorts of nebulas in the sky that are hard to see with the naked eye, but if you could see them, you'd see the sky is a vibrant place, lots going on. Big things bigger than the moon. The Orion Nebula is bigger than the moon in the sky. And so I did this exercise. Now you're not in. Stop it, Kat. So you'll do this exercise. When we were in class, I did the exercise of measuring the distance between me and the students and the angles that things subtended. And so you could figure out, for example, if you're sitting in the back of the class, if the moon and sun were this size, here's how big the Andromeda Galaxy would look in the night sky. Here's how big the Large Magellanic Cloud would look in the night sky. Here's how big the Orion constellation would look, right? And there's lots of things I didn't include in here, right? Whenever there's a supernova, it produces this big expanding ball of gas. There's supernova remnants all littered throughout the sky that are larger than the moon, sun and moon, larger than ½ a degree. So anyways, the sky is actually an exciting place. It's just our eyes tend to not be good enough, especially in city environments where there's lots of light pollution, to clearly see all the cool stuff that's going on in the sky. Okay, so I'll end this lecture, then move on to another topic by just, using this formula, right? If you want to know how big the Andromeda Galaxy is, and we know, one, how much of an angle it subtends in the sky, so it goes across by, let's approximate it by, say, 4 degrees, okay? And we know how far away it is, okay? Right, it's about 2.5 million light years. Well, we just use this formula. The distance r, 2.5 million light years times 4 degrees. We have to convert radians to degrees here. We get 1.7 times 10 to the 5th, which means 170,000 light years across. So that's how big the Andromeda Galaxy is, similar to how big the Milky Way is. Okay, hundreds of thousands of light years across. Any questions on this second lecture? Now we're going to move on into the third. Okay, so this third lecture is about lunar phases, eclipses, ancient astronomy. So we're going to talk about one of those big things that everyone's noticed since forever. Probably one of the first things is the moon and its phases. And then we'll talk a little bit about another major phenomenon that people have recognized for thousands of years, which are eclipses. So Here's a picture of the moon from the Mars Reconnaissance Orbiter. So it's cool seeing images where both the Earth and the moon are in the exact same frame. So the Mars Reconnaissance Orbiter turned his telescope back towards Earth, and you see Earth and the moon. And what you see here is that even the Earth has a phase, right? It's not just the moon that has a phase, right? Whether it's a quarter moon or a full moon. The Earth has a phase too, right? If you're standing outside of Earth, right, like this Mars Reconnaissance Orbiter is, and the phase just has to do with where the sun is relative to sun. You see, the sun is off to the right in this picture, and so it's illuminating the right side of the moon and the right side of the Earth. And you can imagine as the Earth spins, right, might become night and day, right? You're on the surface of the Earth, so you might spin around so that you can't see the moon anymore, or you might spin around some more and it appears to rise and set from your point of view. But as it rises and sets at a given time and it's the moon's orbit around the Earth, you will see a given phase of the moon because there's a given relationship between the moon, the Earth, and the sun. Here's another image. This one is from a Chinese mission to orbit the moon. So this is this Chinese orbiter that actually recently a descendant of this orbiter scooped up moon rock, brought it back to Earth. Okay. This is their first one where they just orbited around the moon. So another nice picture of both in one frame. And here's one if we really just scale. So we scale out. So I've done this digitally. But this is just a picture of the Earth and moon in one frame where you see everything correct, everything to scale. Okay. See the Earth on the left, moon on the right. So usually, often when you see the moon and the Earth, it's a cartoon, a depiction, because you don't actually want to draw them to scale because then it's hard to see them. But here's an accurate depiction. As you can tell, when it's to scale, the moon's pretty far, right? It takes like 12 hours to fly across this far in an airplane, right? Right. There's many Earths distance between Earth and the moon. So it took the astronauts, right, in the Apollo missions several days, going very, very quickly to get from the Earth to the moon. Okay, so let's talk about the phases of the moon. That's one of the first things in this course I really want you to understand. One thing to understand is that the shape or the patterns you see on the surface of the moon always stay the same. And that's because we always see the same face facing it. Now, that's not because the moon doesn't rotate. It does rotate, but it rotates in what's called a synchronous revolution and rotation are synchronous. And we'll talk why this is later. It's due to the tidal effect. But essentially, the moon rotates at the same rate as it orbits the Earth. So for every one moon rotation, it completes one orbit around the Earth. So always the same face. It's rotating just fast enough that the same face always points towards the Earth. Okay. Now the phase of the moon has nothing to do with the face of the moon. It's just how much of the moon is illuminated by the sun. Okay. So some terminology here, right? You can have the phase of the moon is increasing. That's waxing. In other words, the moon is the amount of light on the moon over the course of the month is increasing and increasing towards a full moon. Okay? You can have a waxing crescent, so that it's just after a new moon. It's starting to get, the crescent moon is getting larger. Or you can have a waxing gibbous. And I like that word, gibbous. It sounds like what it means, like kind of a rotund moon that's edging towards being full. It's a waxing gibbous. Okay? And you can have decreasing illumination. So after a full moon, you get a waning gibbous. Further along, you start reaching the crescent. You get a waning crescent moving towards a new moon. And a new moon means there's no light. The moon is totally in these, the face that you're seeing of the moon is in shadow. So here, we can get a really good understanding of the phases of the moon by just using this cartoon where we imagine here's the Earth. Okay, and remember the Earth is rotating, so all the while, every 24 hours, you're on a place on the Earth, so you're rotating, so you see the moon rise and set, and you see daytime and nighttime. But it takes much longer than a day. It takes a month for the moon to orbit the Earth. So at any given time of the month, the moon might be here, say. Okay? And if the moon is here and the sun is off to the right, well, what will you see? Well, you will always see the moon half illuminated. Okay, that's called the first quarter. Okay. So here, the moon is half illuminated by the sun. It's the first quarter. Now you can tell a little bit more though, just from this diagram. Not only can you tell that if you're, now depending on the time of day for you, it might be that you're over here, so you don't see the moon at all. But if you are, say, it's the time of day for you, such that you see the first quarter moon straight above you at your zenith, right, high in the sky, what time of day would it be? Well, you can tell from this diagram because the phase of the moon is the same as the phase of the Earth, really, from this point of view. In other words, if you saw that first quarter moon right above you, you would be standing here, which would mean that for you it would be sunset, right? You're on this line here between the light side of the Earth and the dark side of the Earth. It's sunset. Okay. Similarly, if you were to say, let's keep it where you're standing here and it's sunset for you. What if it was a new moon? Where would it be located? Well, if it was a new moon and it was sunset for you, you would have, if you're going to see it in the sky, it would have to be at the horizon. You'd have to be looking this way. Similarly, for a full moon, you have to be looking this way towards sunset. I mean, towards this would be towards sunset. This would be towards away from sunset. Okay. Let's take another case. Say it's midnight and it's a full moon. Well, if you're standing here, so it's midnight, that full moon will be straight above you at your zenith. Right? So here's the moon on the opposite side of the Earth from the sun, so it's fully illuminated. It's a full moon. And if it's midnight and you're standing here, you'll see the full moon straight above you. Now, it tells you also that you're never going to see a full moon at noon, right? You're never, I mean, you do see the moon sometimes in the daytime, but you're never going to see a full moon at noon because of this diagram. It clearly shows that at noon, the full moon has to be on the other side of Earth or to be fully illuminated. Okay? So this sort of cartoon, this picture tells you a whole lot about the phases of the moon and where you expect to see them in the sky at a given time of day. So here's a question for you. Kind of a different one. We just kind of went over it. So let me ask this. This is one of the sort of questions I would like you to be able to reason through. So it's 6 a.m. Okay, so it's sunrise. You look up in the sky and see a moon with half its face bright and half its face dark near the upper meridian, meaning near the zenith. Okay? What phase is it? Ten more seconds. Okay, so just barely people got the correct answer, first quarter. So I'll go back to this picture here. So first quarter, I'm sorry, people just slightly got it wrong. I read that wrong. So yeah, this would be the last quarter, right? Because it's sunset, not sunrise. I mean sunrise, not sunset, right? So you would have to be standing here, right, where it's sunrise. Okay, and if you looked up, straight up, and saw half full, meaning quarter, it would have to be the last quarter. Whereas if it was sunset, you'd see the first quarter. I understand why people would get half correct, half wrong on this one. At least most people seem to know that it wouldn't be a gibbous, and you wouldn't call it a half moon, it's called a quarter moon. Okay. Now, the origin of the idea that we divide the year up into 12 months has to do with the moon's orbit. Right? And we're going to talk in detail about this. In fact, you might think it's too much detail, but it'll be important to understand eclipses. So, when the moon rotates, first of all, in order to make sure that one side faces us all the time, it's about 29 and a half days. So its rotational period is about 29 and a half days. It's about a month. Okay? And that's roughly speaking how long it takes the moon to orbit the Earth. A month. As we're going to talk about now, there's a number of different ways you can define that to mean. So one way is called, and this is called the sidereal month, or the sidereal period, derives from Latin for sidus, for star. And this is defining a month to be the time it takes the moon to complete one full orbit of the Earth with respect to the stars. Okay, so this isn't thinking about the phases, in which case you need to include the relationship between the moon and the Earth and the sun. It's just talking about with respect to the stars. One full orbit takes 27.3 days. So if you were to define a month based on how the moon moves with respect to the stars, one full orbit, this is what most people might think of as an orbit, would be 27.3 days. But there's another also compelling definition of month, which is called the synodic month, from Greek word meaning to come together, which is just how long it takes to go from full moon to full moon, or from new moon to new moon, which this is also often what people think of when they think of how the moon relates to a month. It's because you get one full moon every month. Well, not quite. So the synodic month is a little bit longer than the sidereal month. And this makes things difficult for trying to figure out how to define a month in terms of the moon's orbit. So, and we'll see in a second why this is. So it takes a little bit longer to go from full moon to full moon than it takes for the moon to complete one orbit with respect to the stars. So here's why that is. So suppose the moon starts here. Suppose it starts as a new moon. Okay, so the moon is between the sun and the Earth. So that means that if you were to look out at the new moon, it would, this side would be in shadow. That's what a new moon is. And if we were to complete one month, one synodic month, sidereal month, that is with respect to the stars, then we'd come back to this diagram with the dashes, okay? Right? So with respect to the stars, it's completed exactly one full orbit. So it comes back exactly to where it was before. But, so this took 27.3 days. But you'll notice that it's no longer a new moon. And the reason why is because in that month, the Earth has moved with respect to the sun. So even though this moon is in the same place with respect to the stars, so it's still pointing in the same direction. The Earth, moon direction is pointing in the same direction. Now, if you look at the sun, the moon is no longer aligned between the Earth and the sun. So it's no longer a new moon. You actually have to wait another couple days, a little bit more than a couple more days, for the moon to keep orbiting into alignment to produce another new moon. So then with these dots, this is where the orientation would be set to the new moon is back in between the Earth and sun. So that takes another little bit more than 2 days. So a synodic month then is 29 and a half days. That's the time it takes to go from new moon to new moon or full moon to full moon. So that's going to come into play. Another thing that's important to think about is that when the Earth rotates, like once every 24 hours, of course it appears like the moon rotates around us, right? But it doesn't really, right? It's in fact, the stars also move around us every 24 hours. So, but also once a month though, the moon really does move with respect to the stars. So at a much slower rate, the moon really is moving. And so, let's see. So first of all, in the sky, due to the Earth's rotation, the moon moves about 15 degrees every hour. That's actually quite a bit. So remember, that's more than a fist. If you put out a fist, right? A fist is about 10 degrees. And look against the sky, the stars and the moon all move about 1.5 fists every hour, okay? But what about the moon with respect to the stars? So one way of thinking of this is the celestial sphere, right? The moon along the celestial sphere. Which stars is the moon blocking out along its path? Well, because the moon moves 360 degrees, in 27.3 days, that's the sidereal month, it moves about 13 degrees per day, which is about half a degree per hour. So that means if you do look over the course of an hour at the moon in the night sky, okay, the moon and the stars all move by about a fist and a half in the sky, but the distance between the moon and the stars changes by about a full moon width every hour. So the moon is tracing across the celestial sphere, or across the stars themselves, one full moon width about every hour. And that's due to the fact that the moon itself is orbiting once a month. It goes all the way around. Now, we're going to talk about how do we make sense of the fact that the sidereal month is not the same as the synodic month? That is, how do you make a calendar when you want at the end of the day to have these two things match, right? If you want a month, I mean, the moon completing orbits with respect to the stars, and also the moon going from new moon to new moon, full moon to full moon, but they don't quite match. How do you make them match? Well, here's an analogy that is the way you can make it work. This is called the Metonic cycle. We're going to talk about him in a second. In ancient Greek, when they came up with a calendar to deal with this issue. Suppose you have two runners, okay, and these are analogous to these two orbital speeds. Suppose you have runner A going around a track, red, who circles the track once every 3 minutes. So runner A is pretty fast. Runner B isn't quite as fast. It takes runner B 4 minutes to circle the track. Okay. How often does the scene repeat itself, right? How, like if they pass each other, how long do you have to wait for them to pass each other again? Okay, the answer is 12 minutes. And the reason why is because the faster runner can go around 4 times. That takes 12 minutes. But also, the slower runner can just go around 3 times, because 4 times 3 minutes is the same as 3 times 4 minutes. So every 12 minutes, they'll pass each other again. Okay? And that's the key to understanding how you can fit together. And this is kind of one of the famous ancient calendars utilized this fact to construct a calendar in which you can kind of fit these 2 months, these two ideas of the month together. So the Metonic cycle notes that 1 year is about 365 days. Okay. Now 12 synodic months, okay, that is going from new moon to new moon, or full moon to full moon, doesn't quite make a full year, unfortunately. Okay, that's only 354 days. So you can't really do a great job of making a year out of 12 synodic months. So you're off by about 10, 11 days per year. But after 19 years, that adds up to 206 days, which is almost exactly equal to 7 synodic months. So if you want to keep what you would call a lunar year, that is a year defined by going from full moon to full moon to full moon to full moon, and if you want to keep that in sync with what we call the solar year, having to do with how things orbit with respect to the stars, then you add what's called an intercalary, or like a leap month, on 7 occasions over the course of a 19-year period. That is, every 19 years, you need to fit in 7 extra months in order to make everything match up. Okay. In other words, 235 synodic months is equal to 254 sidereal months. And that is 235 synodic months means 235 full moons. Okay. Whereas sidereal months are the months with respect to the stars. This was named after the Greek astronomer Meton of Athens, 400 years BCE. Right? He noted that every 19 years you get 235 full moons. And so he popularized the cycle. It was already used by the Babylonian calendar and ancient Chinese calendar systems. Okay, this became one of the important ancient calendars starting in Greece as well. Okay, and the idea is that every 19 years, the position and phase of the moon in the sky will repeat. just like those two joggers going around the track. Now, because of this, right, because the calendar year, right, which is 365 days, so going back a couple slides, includes 12 full moons or 12 new moons, but plus an extra 10 days, that means that there's 10 extra days in a year where you could get another full moon, okay? That's called a blue moon, okay? It means rarely. It has nothing to do with the color of the moon. Blue moon does not mean the moon is blue, but it means getting an extra full moon in a given month. So sometimes you get 2 full moons in a month, and that's because of the fact that the synodic month is different from the sidereal month. So typically, you say there's a blue moon if you get 2 moons in a month, and you can't get that in February month because the synodic month is 29.5 days long. So that means that that means that blue moons are going to be pretty rare, and they can't happen in months that are like 28 days long, like February. You can only fit 1 full moon or new moon in February. And historically, also, a blue moon referred to the 13th full moon in a year that happens every 7 times every 19 years. Okay? So on average, you get a blue moon once every 2 or 3 years. Any questions so far about phases of the moon, blue moon, months? So there's another way. So I'm going to actually end up with 4 definitions of a month here, because there's another important sense in which the moon's cycle repeats roughly every month, but it's slightly different. And that's because of the fact that the moon in any planet's orbit is not exactly circular. In fact, every orbit, as we'll talk a lot about in depth later on, is an ellipse. And that is, and this is way exaggerated, but every orbit has an apogee, meaning furthest from the, in the case of the moon, furthest from the Earth, and perigee, closest to the Earth. So the moon every month gets furthest from the Earth and then closer, further, closer, further, closer. And that has the effect of the moon being a little bit larger in the sky and a little bit smaller in the sky. Okay, so this was not to scale, just to show you the point. But this is the actual change. It's not very much, but it's enough to still be important. So here I have like a circle shown in a dotted line, but the actual orbit is an ellipse. It's kind of squeezed a little bit. The perigee is about 360,000 kilometers, whereas the apogee is about 400,000 kilometers. So there's a fairly significant difference between the perigee and apogee of the moon. And as a result, right, it changes in size over the course of a month. So at lunar perigee, when it's closest to us, it's this big. Compared to lunar apogee, it's measurably smaller. Okay, you tend to not really notice it that much, right, with your eyes, but as you can see, it actually is pretty significant if you compare them side by side. Okay, and why isn't this month, though, the idea from going a little bit closer, further away, a little closer, a little further away? Why isn't that the same like as the sidereal month? Well, the reason why it's not exactly the same is because the elliptical orbit of the moon precesses. Okay? It precesses and completes one precessional orbit every 9 years. So what precession means is that it completes an orbit, but is just a little bit off. It a little overshoots. So it doesn't actually get to the exact same position with respect to the stars as it was before. And so it keeps precessing around. And then every 9 years, it does get back to where it was before. And this is caused by tidal forces, something we'll talk about. It's due to the influence of the sun's gravity. Okay. And so what this means is that the what we call anomalistic month is slightly different, just a fraction of a day different from the sidereal month. So we call this the anomalistic months, perigee to perigee or apogee to apogee, right? Largest to largest or smallest to smallest. Slightly longer. Okay, PHYS is longer than the sidereal month. Okay. Okay, now we're going to talk about one more definition of month, and this will also be important, which is that this is due to the fact that the moon's orbit is tilted. So, right, so we start off thinking about the simplification that the moon and sun and earth are all in that same plane that we call the ecliptic. So when you draw a cartoon, we're just looking from top down and we see the moon, the sun, the earth. But in reality, this is all in 3 dimensions. And the moon is close to the ecliptic, but it's not quite, okay? Its orbit is 5 degrees inclined to the ecliptic. So if this is the earth and sun ecliptic, the moon's orbit is tilted 5 degrees out of that. So it passes in below the ecliptic, above the ecliptic, below the ecliptic, above the ecliptic, just like you see in this picture. And that orbit going below, above, also isn't exactly the same as the sidereal month. Okay, it is called the draconic month. Okay, which is slightly shorter than a sidereal month, 27.221 days. All right, and that again has to do with the relationship, gravitational relationships between the sun, the earth, and the moon. Okay, so this additional month is we often talk about either furthest down to below the ecliptic to above to below, but in practice we usually say node to node. How long does it take to pass through? So pass through the ecliptic in the ascending node, you pass through in the descending node, and then you pass through up to the ascending node again. How long is that? That's one draconic month, just slightly shorter than the sidereal month. So far we've talked about, and this is all 4 definitions of months. We have one, how long it takes the moon to orbit with respect to the stars. One is how long it takes to go from new moon to new moon or full moon to full moon. So that's just kind of one of appearances. Then we have one for how long it takes the moon to go from being closest to us again, or furthest away from us to being furthest away from us again. And finally, how long it takes for the moon to orbit from being within the ecliptic to being out and above it to below it to being back within the ecliptic again. Any questions about definitions of months? So I mentioned kind of a simplified picture before about the fact that one side of the moon always faces us. It's slightly more complicated than that. So we do actually see a little bit more than 1/2, and I'll show you a video in a second. Now our first full view of the far side of the moon was we only saw that in the 1960s when we sent out lunar probes, right? But over time, if you sit and watch the moon over a month, you do see slightly more than half of the moon. This is just due to what's called libration, the slow rocking back and forth of the moon as viewed from Earth. Okay, it was caused by the fact that, right, things like the fact that as the Earth rotates, you're seeing the moon from slightly different vantage points. Right, you're in 3 dimensions. You see slightly to the left of the moon, slightly to the right. Some of it's due to the fact that the moon's orbit is a little bit eccentric. Okay, so it's orbiting in slightly different places. Okay. Here's a video to get it that shows over the course of a month kind of that rocking motion. Oh no, they got rid of it on Wikipedia. That's really annoying. Okay, I'll have to fix that. I could probably just Google it, but I'll encourage you to Google it yourself, libration. Okay. But what you see over the course of the month is the moon face. It just rocks back and forth, so you see a little bit more than 50% of the surface. And there's another important point as we go through. I'll give examples of, let's see, someone else already. Someone asked whether this is still part of chapter 2. I think this is chapter 3. Wait, no, maybe it is part of chapter 2. I guess this is still part of chapter 2 that we're talking about. We're going to get into chapter 3 today. That's why. So this is on the border between 2 and 3. So one thing I always want to point out whenever we're talking about things that could be calculated is NASA provides calculators for all of this. So if you ever want to know, right, what is the phase of the moon now? What are all of these things? What's the, where is it in its orbit with respect to the sidereal month, synodic month, draconic month, anomalistic month, right? How close is the moon to us? What's the phase? Where is its position going to be? All these, NASA of course tracks all of this, including libration, right? So there's a measure for how much it's rocked toward you, and so on. Okay. As well as the position of the so-called horns. Now we'll talk about these in a second, but you don't see the horns right now because it's not a crescent. But when it's a crescent, the so-called horns of the moon point away from where the sun is. And depending on where you are on Earth and the time of day, you'll see the horns pointing in different directions. Okay, any questions before we talk about eclipses? So this is why we went in such detail about months, because that's really important for understanding eclipses. So first of all, terminology. Okay, a lunar eclipse is the Earth's shadow on the moon. This is when the Earth gets in the way of the moon, and the moon is in Earth's own shadow. Okay? And so for that, you need what's called syzygy. You have to have the sun, the Earth, and the moon in exact alignment for that to happen. And the solar eclipse is the exact same, but for the moon's shadow on the Earth. Okay, so in either case, whatever is casting the shadow, whether it's the Earth or the moon, it creates 3 regions that's important to understand. The penumbra, shown in gray, the umbra here, and then after the umbra passes through a point over here is called the antumbra. And if you were standing out here looking back towards the Earth and sun, these are what you would see. An umbra is the region of shadow where you would see a total eclipse. Okay, that's why it's shown as darker here, because it's totally in shadow. Okay, whereas the penumbra are regions of partial eclipse. If you are in this region, you look back towards the sun, you're not in full shadow, you're in partial shadow. Right? So it's blocking some of the sun's light, so it's a little bit darker, but it's not totally dark. The antumbra is when you're so far away that the moon or the Earth, depending on what you're looking back at, doesn't completely block out all of the sun. It's not big enough, right? You're far enough away that due to the angular size of say the Earth, it's only covering the inner part, say, of the sun. So you only get a full solar eclipse or full lunar eclipse so a full lunar eclipse if the moon is in the umbra of the Earth, and you only get a full solar eclipse if the Earth is in the umbra of the moon. Okay, here's a picture of a moon going through different stages. So here you are looking towards the moon as it is going through a lunar eclipse. And this is the case where the moon is in the penumbra, right? So the moon is is receiving some of the light from the sun, but not all of it. And you get this really nice kind of change where suddenly the moon looks rather spectacular and kind of actually looks orangey and interesting when you get to the full lunar eclipse, because the moon is totally in Earth's shadow. It's in the umbra of the Earth. Now, so we're going to get to the complication in a second. So, but let's consider this cartoon where we're imagining for a second that this is all happening in 2 dimensions in the ecliptic. So in 2 dimensions, you would expect that there would be eclipses. You'd expect actually 2 eclipses every month. Okay, every month, right? The moon is going to orbit at some point behind the Earth here, which is what causes the full moon, right? You get a full moon when the moon is over here, and you'd expect the moon to just walk right into the Earth's shadow, right? So every month you'd expect a lunar eclipse, and when the moon went this way, it would block out the light from the sun towards the Earth, and you produce a solar eclipse. Okay? So what you would see, right? You would see every month, you would see the moon moving into the penumbra, and it would become a partial or penumbral eclipse, and then it would move into a total eclipse, a partial eclipse, and then a penumbral eclipse, and then out. Right? So you would see all of those stages, but of course, in reality, we're in 3 dimensions, and the moon is not in the same ecliptic. So otherwise, we literally would see 2 eclipses, 1 solar, 1 lunar, every month. Okay, but we don't, because remember, the moon is not in the same plane. It's tilted by 5 degrees from the ecliptic. So sometimes the moon is below the ecliptic, sometimes it's above the ecliptic. In order to get an eclipse, you have to have the luck to have the moon also at the right time have passed down into the ecliptic. So this is what this is showing. Sometimes you don't get an eclipse, and you're in this region, you're about to get an eclipse, but you're above the ecliptic, so you don't pass into the umbra. Or maybe you're below the eclipse, you don't pass through the umbra. Okay? And in order to get an eclipse, you have to have the moon passing. Here it's showing a descending node. Okay, to get a lunar eclipse, you have the descending node in this case, as the moon passes down through the ecliptic at just the right time. And that could happen so that you only get a partial eclipse, right? It never goes all the way through into the umbra. Or you could get really lucky, and this is why total eclipses are rarer than partial eclipses. And it goes straight through, and you get first a partial eclipse, and then a total eclipse, and then partial eclipse, and then it exits. And so imagine the moon moving down, passing through. Luckily, not only is it passing behind the Earth like this, but it's also passing down through the ecliptic. So it passes from partial eclipse here down into an umbral or total eclipse, back to partial eclipse. Okay, and just like for NASA and other agencies, this is again though NASA keeps track of these. So you can go to their page and for any point on the Earth, calculate for where what are you going to see for a partial or total eclipse. So here's a total eclipse. So it shows the moon passing down and its descending node through the region where you just get a penumbral eclipse, the partial eclipse.
I thought you don't have PHYS on Monday and Wednesdays.
Did someone say something? I couldn't quite
No,
hear.
it didn't.
Hello? Someone may have needed to mute, or I didn't hear you if you're asking a question. Okay, so anyways, this gives a lot of information. It gives 72 minutes in total eclipse at this point. And it gives the other regions where you can also expect to see a total eclipse, the date, and so on. So all of these are calculatable because these are all this is all physics that we understand very well. The orbit of planets, we can all calculate those hundreds and hundreds of years into the future. The rotation rates, everything we know very well. Now, solar eclipses, right? It's the exact same idea as the lunar eclipse. But remember, the moon is smaller than the Earth, okay? And because the moon is smaller than the Earth, it casts a smaller shadow. So kind of here's the picture, right? There's actually a very small region on Earth where you can see a total solar eclipse because here's the moon between the sun and the Earth, and the umbral part of its shadow kind of paints like a tiny little point on the surface of the Earth. Now the Earth is rotating, so as the Earth is rotating and everything else is getting into alignment to get that total eclipse, the Earth is rotating, and so You can imagine this shadow kind of carving a path across the surface of the Earth. That's the path across the surface of Earth, where if you're standing there, you would be able to see a total solar eclipse. Now, for those of you who have not seen a total solar eclipse, or for those of you who have only seen a partial solar eclipse, they really are worth seeing. They are remarkable. And when I say they are worth seeing, I mean a total solar eclipse. There's no comparison between a total solar eclipse and a partial solar eclipse. There's a huge difference that happens when the sun goes into total solar eclipse that is a remarkable experience. Pretty much everyone that sees one kind of agrees that it's just a really remarkable experience. So I highly recommend you try to see one. There was one a few years ago where if you drove down to the southern tip of Indiana, you could see it. Unfortunately, I had to be at a conference that year in Canada, so I was in the wrong direction, so I saw partial eclipse. But as we'll see in a second, there's another one that's coming up in a year or two, a couple years, that coincidentally, also if you drive down to the southern tip of Indiana, you'll be able to see it. So I highly recommend doing so. Ways you can get not a total solar eclipse, a partial solar eclipse, right? If you're in this penumbral region, right, the kind of gray area, if you're in that region, you'll see just a partial solar eclipse, and again, not super exciting. And if you're in that perfect region, but it happens to be that you're at the place in the moon's orbit where the moon is a little bit too far away from the Earth, right? Then the moon will be too small, and you'll get an annular solar eclipse, which is not a total eclipse either. Okay? So you really have to get lucky. Not only do you have to have the conditions for the eclipse, the syzygy that we'll talk more about. You also have to have syzygy with respect to the we call the anomalistic month here, how far away the Earth is from the moon. Okay, you have to be just in this tiny pinpoint along the surface of the Earth that's in the moon's shadow. Here's one example of just a kind of a bunch of photographs as you watch the solar eclipse happening. You watch partial solar eclipse, and then there's a sudden change. That's brief, but that's the really remarkable thing. That's what you're waiting for, is the total solar eclipse. Suddenly, it's like it's night. The birds are going crazy. Eerie, very interesting experience. Okay, so the conditions for syzygy, right? This is what you need to have a total solar eclipse: is have a straight line configuration of the Earth, Moon, and Sun. And so you need to have two conditions, right? It has to be, first of all, it has to be full moon, right? To have a lunar eclipse. That is, the moon has to be on the far side of the Earth from the sun to get a lunar eclipse, and to get a solar eclipse, it has to be new moon, right? And that's what we were talking about when we were talking about this. If that were the only condition, you'd get one every single month, right? But additionally, the moon must be near one of the 2 points where its orbit crosses the ecliptic plane, either the ascending or descending node, as it passes through the ecliptic plane. Again, because the moon's own orbital plane is inclined with respect to the ecliptic. And then, in order to get a total eclipse, you also need to consider, so there we're considering both the synodic and the sidereal months. Those have to align, but additionally, you have to consider the anomalistic month, perigee to perigee, because if you want a total eclipse, you want the moon to not be too far away from the Earth. You want it to block out all of the sun. Here's a cartoon just showing two examples where you don't have syzygy and two examples where you do. Right, so here, right, so of course you can have the moon be in the wrong location, but let's assume that we have, say, a new moon or full moon in this location of the Earth and Sun on the right. But here you see that the new moon is above the ecliptic, so you don't get in this case, a solar eclipse. Here the full moon is below the ecliptic, so you don't get a lunar eclipse. And if the moon is here, you don't get either, because of course the moon is just not in the right place in its orbit. Same over here. Here for the you don't get a solar eclipse because the moon is below the ecliptic. Here you don't get a lunar eclipse because the moon is above the ecliptic. Okay. But in these two examples, you have the this situation just right. You have here, when the moon is on the far side of the Earth from the sun, you can get a lunar eclipse, because, as you can see, it's here in the ascending node, passing through the ecliptic, so just creating perfect syzygy. Similarly, if the moon were to be here, it would create a solar eclipse, because you have syzygy. Similarly here. Any questions about this concept of syzygy and how you get solar eclipses or lunar eclipses? Okay, so it turns out that there's just a few times of year when you can have an eclipse. We call that eclipse season. This is due to that 5-degree inclination of the moon's orbit. So if I go back here, right, you see that there's only a couple times a year, generally 6 months apart, exactly as you would think from this picture, when you can have syzygy. And that combined period is about 30 days. But you can get eclipses that are, so you can get eclipses that are 1 month apart. That happens about 11% of the time. You can have eclipses that are 5 or 6 months apart, and that occurs most of the time. But these successive ellipses, when you get a successive ellipse, just 6 months apart, say, these tend to be totally dissimilar. Meaning, if you're going to see them, you're going to be at totally random, different places on the Earth. Right? You may be wrong side of the Earth, wrong time of day, right? Also, you may have to travel very far to see it, and so on. But so I gave this previous example for the Metonic cycle, where we had 2 runners. You can do the same thing with 3 runners. And that's what you need for a total solar eclipse. You need not only the synodic, sidereal month, but also the anomalistic month, all to create a coincidence. So suppose you have one eclipse, a really nice total solar eclipse, and you want you want to calculate how long it takes for that exact same eclipse to repeat itself. Well, here's an analogy similarly with 3 things going on, 3 runners. So you have one that takes 3 minutes to run around, one takes 4 minutes to run around, one takes 5 minutes to run around. Well, just like before, we can find the fact that every 60 minutes in this case, they will all meet up again, because 20 times 3, so 20 laps for the fastest runner, 15 times 4 for the middle fast runner, or just 12 laps for the slowest runner, all takes exactly 60 minutes. And so they will all meet up in the exact same configuration every hour. They keep running around this track. So similarly, we have these 3 months. We have the synodic month, new moon to new moon, which is 29 days, and the anomalistic and Draconic months that are slightly different, each 27 days in a bit. And it turns out that about 223 synodic months is about 242 Draconic months, which is about 239 anomalistic months. Okay. In other words, we call this a seros. Okay. 1 seros is 223 synodic months, or 18 years and 11 days. So every 18 years, an eclipse will repeat the exact same eclipse. So this is nice. This means that we know that if you get a really perfect eclipse, 18 years later, you're going to get it. And here's a picture of just some example eclipses 1 Saros apart. So first of all, so here's the one that happened a few years ago in 2017. So this shows its path across the Earth. Now remember, imagine that umbra, that shadow of the moon on the Earth as the Earth is rotating. And the Earth is curved, so that's why it creates this kind of curved path. And so this is why you had to go down to southern Indiana, right? You had to drive from Chicago up here down to southern Indiana to get into that path. 1 Saros, 18 years later, you get another identical eclipse. Now it's not in the same place because meanwhile the Earth is rotating. So, so where you are with respect, the rotating Earth under that ellipse, that's that shadow carving into the Earth, puts you at a different location on this. So here it's going to bless some of China and Japan. Okay. Here's the one I mentioned a few years later. So in 2024, so 3 years from now, there's going to be another really nice eclipse that just totally coincidentally, you see, kind of crisscrosses. Very similar location. I think, again, you have to drive to the southern tip of Indiana to see it again. But one Saros after that, you get another one. So 18 years later. And so anyways, this is just a bunch of Saros pairs shown in different colors. Here's an example, just one Saros called Saros 136. So just one Saros every 18 years, you see where it goes on Earth. So you see it, it moves around this way because the Earth, meanwhile, is rotating, but also it moves up and down in latitude on the Earth because, remember, the Earth is tilted. So 18 years and 10 days later isn't exactly going to always be the same season. Over time, that those 10 extra days are going to add up, and you're eventually going to, right, because the Earth is tilted, it's going to be in the northern hemisphere, then it's going to be in the southern hemisphere eventually. All right. Any questions about eclipses? So for the rest of the lecture, let's talk a little bit about science and the ancient roots of science itself. So first of all, there's some things that we all kind of take for granted. So one thing, our units of time are astronomical in origin. So let's talk a little bit about that, right? So a year, right? We take for granted a year. Well, of course, a year has certain features that you might recognize, like winter recurs every year, summer recurs every year, the seasons. Okay, that has to do with the fact that the Earth is tilted, remember, and 1 year is one orbit around the sun. So a year is one orbit around the sun, and because of the Earth's tilt, remember, one half of the year, one side gets more light than the other side. That gives rise to the seasons. So for thousands and thousands of years, people have recognized what a year was, more or less. They didn't necessarily know that the Earth was going around the sun as opposed to the sun going around the Earth, but they understood that that was what was happening, that there was one cycle with respect to the sun and the Earth that caused the seasons. A month, right? We just spent a lot of time talking about months, right? It's roughly the time it takes for the moon to orbit the Earth. And we just went into a lot of detail that you can define that in different ways. So roughly a month is new moon to new moon or full moon to full moon, but that's not quite the same as a month going one full orbit of the moon with respect to the stars. Okay. Week. Well, 1 day was given for each of the ancient planets, meaning other than the stars in the sky, what were the other celestial things that they could observe? Really obvious are the sun and the moon, okay? Sunday and Monday. But then there's others like Mars, okay, like Venus, like Saturn. So we'll talk about that in a second. The day, okay, a day was the time it took the Earth to revolve on its axis. Now they didn't understand that at first. They didn't think the Earth was rotating, but that was the day, and how long it took the moon to orbit, to appear to move around the Earth, the sun every day around the Earth, and the stars every day around the Earth, every 24 hours. Okay, and further, an hour was defined to be a 12th of daylight. So by the way, you step back, every single one of these is astronomical in origin. It's kind of neat, right? Hour, day, week, month, year, all have to do with astronomy, which makes sense because this was one of those regularities that people could observe with their eyes every single day of their lives without any special technology or telescopes. You could see this. You could see all of these. So the 7 days a week, for example, right? Sunday, origin is sun. Moon, Monday. Mars, origin Tuesday, right? Martes, Mardi in French. Mercury, associated with Wednesday. Jupiter, Thursday. Venus, Friday. Saturn, Saturday. These are the 7 astronomical objects that everyone in ancient times was able to know, right? They could see Jupiter. It was like any other star, bright star, but it moved against the background of all the other stars because it is different from stars. It moves against the background of all the other stars across the celestial sphere, we could say. Okay, right, and it traces back, more than 3,000 years ago when Babylonian astronomers assigned days of the week to what they called the planets. Okay, and time, right? Time of day. So here's an Egyptian obelisk. This one has been relocated, but right, these Egyptian obelisks are the origin of our modern clocks, essentially, right? They can be traced back to tracing the day, so 12 hours of daylight into 12 pieces over 4,000 years ago, right? This is a sundial, basically, right? It makes sense, too, that they would divide it into 12. 12 is a really nice number because it's a number that's divisible by a lot of other numbers, 2, 3, 4, and 6. That means you can easily divide it in half, into thirds, into quarters, into sixths. And by the way, the origin of AM and PM. AM stands for ante-meridium. Okay, the sun is before reaching the meridian. PM is post-meridian, after the sun has passed through the meridian. So all these are astronomical in origin. And again, because you didn't need any special technology or instruments to observe all of this stuff we've just been discussing, phases of the moon, eclipses, right, stars, right, the seasons. Astronomy was the backbone of many ancient social, political, religious systems. Right, ancient astronomers noticed these patterns and built structures to mark the seasons. Right, that was incredibly important for planning crops, for example, to know when there would be rain. So they aligned structures with the solstices, which could tell you about the seasons. You navigate, right? We talked some about navigating using stars. If you could predict eclipses, that was of significant religious significance. I mean, even what we know today, as I mentioned, if you see a total solar eclipse, it's pretty mind-blowing. And if you could predict that thousands of years ago, you could wield significant amount of religious or political power. And they could, right? These were smart people that were able to figure out much of what we've just discussed. Here's an example of predicting the rain. You can predict the rain. So, for example, people in Nigeria for 1,000 years have predicted the rain by looking at the horns of the moon. So I mentioned this because of the fact that the Earth's orbit is tilted. Depending on where you are on Earth, you see the so-called horns of the moon pointing in different directions at different times of year. So these horns of moon, so here they're pointing straight up. We call that 0 degrees, plus 15, they're pointing to the right, minus, they're pointing to the left. And for them, in June and July was their wet season. So for them, the moon horns pointing up meant that was the wet season, and the dry season would be when they are not pointing up. Stonehenge, right? This is another classic example where the alignment of the stones allowed the sun to come through certain gaps in the stones only at certain times of year. For example, at the solstice, that is the time of year when the day is longest or the day is shortest, marking out the seasons. Now, the roots of scientific thinking, what we call scientific thinking, are based on everyday notions of observation, right? Critical thinking, trial and error, experiments. And I'm going to harp on some of this, right? It's something that we've only been able to articulate really clearly more recently. It's just how important it is to place on actual observations and not spend too much time thinking that you've got a really great theory disconnected from observations. Because what we've really found out over the years is that a lot of people can come up with some really smart theories, right? It's not that they're dumb, they're really, really good theories, but are just wrong. Because sometimes it's because you can't, right? You can't reason through everything and you make mistakes. But sometimes it's just because that's not how nature is. Okay? Nature is beguiling. Okay. Okay. And so you think critically about your observations and you do experiments. And if the experiments tell you something in contradiction with your theory, You don't want to hold too strongly to your theory for the reasons I just said. You need to be open-minded about being wrong. And so in the history of science, things have been overturned over and over again and improved as people have embraced being wrong. Right, so one of the landmarks, there's a long history, and I can't give you the whole history, but one of the landmarks is the Greek contributions to scientific thinking. Right, of course, they valued critical thinking. If any of you have taken some introductory classes on Plato or something, right, a lot of debate and shooting ideas. They use mathematics. Okay, mathematics gives precision to ideas. You can calculate numbers to predict exactly, say a time of day and year when an eclipse will happen. That's important instead of just making vague statements that can be interpreted different ways. Okay, they created very specific models of nature, right? They may have been wrong, but like say the geocentric model was a very specific model allowing you to make predictions. And they had the beginnings of reasoning from observations. We'll see an example in a second with Eratosthenes. So yeah, let me end by playing you this video of Carl Sagan explaining why the Earth is round, as discovered over 200 BC. So even today, you'll have flat earthers who are making some pretty profound errors in critical thinking. But we've known, not since Columbus, not since 100 years ago, but the ancient Greeks knew the Earth was round, and they knew exactly how big it was. So here's Carl Sagan explaining how we know that. And tell me if you can hear this. Tell me if you can. Someone tell me if they hear this. Yeah, I can hear it.
It seemed immense, but was the only world we could explore. Its true size was first worked out in a simple and ingenious way by a man who lived here in Egypt in the 3rd century BC. This tower may have been a communications tower, part of a network running along the North African coast by which signal bonfires were used to communicate messages of state. It also may have been used as a lighthouse, a navigational beacon for sailing ships out there in the Mediterranean Sea. It is about 50 kilometers west of what was once one of the great cities of the world, Alexandria. In Alexandria, at that time, there lived a man named Eratosthenes. One of his envious contemporaries called him Beta, the second letter of the Greek alphabet, because he said Eratosthenes was second best in the world in everything. But it seems clear that in many fields, Eratosthenes was top. He was an astronomer, historian, geographer, philosopher, poet, theater critic, and mathematician. He was also the chief librarian of the Great Library of Alexandria. And one day, while reading a papyrus book in the library, he came upon a curious fact. Far to the south here, at the frontier outpost of Syene, something notable could be seen on the longest day of the year. On June 21st, the shadows of a temple column or a vertical stick would grow shorter as noon approached. And as the hours crept towards midday, the sun's rays would slither down the sides of a deep well, which on other days would remain in shadow. And then, precisely at noon, columns would cast their shadows, and the sun would shine directly down into the water of the well. At that moment, the sun was exactly overhead. It was an observation that someone else might easily have ignored. Sticks, shadows, reflections in wells, position of the sun, simple everyday matters of what possible importance might they be. But Eratosthenes was a scientist, and his contemplation of these holy matters changed the world, in a way, made the world. Because Eratosthenes had the presence of mind to experiment, to actually ask whether, back here near Alexandria, a stick cast a shadow near noon on June the 21st. And it turns out, sticks do. An overly skeptical person might have said that the report from Syene was in error, but it's an absolutely straightforward observation. Why would anyone lie on such a trivial matter? Eratosthenes asked himself how it could be that at the same moment, a stick in Syene would cast no shadow, and a stick in Alexandria, 800 kilometers to the north, would cast a very definite shadow. Here's a map of ancient Egypt. I've inserted two sticks or obelisks, one up here in Alexandria, one down here in Syene. Now, if at a certain moment each stick casts no shadow at all, that's perfectly easy to understand, provided the Earth is flat. If the shadow at Syene is at a certain length, and the shadow at Alexandria is the same length, that also makes sense on a flat Earth. But how could it be, Eratosthenes asked, that at the same instant that there was no shadow at Syene and a very substantial shadow at Alexandria? The only answer was that the surface of the Earth is curved. Not only that, but the greater the curvature, the bigger the difference relates to the shadows. The sun is so far away that its rays are parallel when they reach the Earth. Sticks at different angles to the sun's rays will cast shadows at different lengths. If we observe difference in these shadow lengths, the distance between Alexandria and Syene had to be about 7 degrees along the surface of the Earth. By that I mean, if you imagine these sticks extending all the way down to the center of the Earth, they would there intersect at an angle of about 7 degrees. Well, 7 degrees is something like a 50th of the full circumference of the Earth, 360 degrees. Eratosthenes knew the distance between Alexandria and Syene. He knew it was 800 kilometers. Why? Because he hired a man to pace out the entire distance so that he could perform the calculation I'm talking about. Now, 800 kilometers times 50 is 40,000 kilometers. So that must be the circumference of the Earth. That's how far it is to go once around the Earth. That's the right answer. Eratosthenes' only tools were sticks, eyes, feet, and brains, plus a cyst for experiment. With those tools, he correctly deduced the circumference of the Earth to high precision, with error of only a few percent. That's a pretty good figure for 2,200 years ago.
All right, so I like Carl's sake. I like his style. I like his corduroy jacket. I'll leave it there for today, and I will see you next week, Monday. Bye.
Thank you.
Thank you. Thank you.
Thank you.
Thank you. Thank you.